if you have a bounded input, if you put in a bounded input to a process, then you should have a bounded output. What is meant by bounded is that it has an upper and a lower limit. Okay, so it has an upper and lower limit. If you have a process, we give it an input that is bounded, let's say a step change, then the output should also be bounded. Okay, so if it's bounded, then that's okay. So if you have the link for the previous Jamboard, then you can go to that Jamboard. Otherwise, I will put the link here in the chat area. Sekejap stop sharing. Okay, that's the link. This is also where you have the discussion for the tutorial last time. Okay, I will share the Jamboard. Okay, sharing Jamboard. Okay, we will do some activities in Jamboard. By the way, when this is what I want you to understand, when you are doing your tutorial, your quiz, or your test, or your report, or whatever you do, you need to put in the exact transfer function in the box. Oops, sorry. You need to put the transfer function in the box. Let me use red. Okay. So this is from your tutorial. This is an example. I'm giving you an example. Okay. So let's say you have calculated GV. You have calculated the process transfer function. You have the disturbance. So you will know what is the disturbance. You will know what is the manipulated variable, what is the set point, what is the measured variable, the control variable, and so on. Please label it exactly using the variable label that you have been using. Okay? And when you derive, please put those numbers in. If you are just deriving and following what's in the book, you are copying the drawing in the book, you will get a 0. Okay? Understand? Yeah? So please do it like what you see here. Yeah? If you go to the previous pages of the Jamboard, okay, that is okay. I will just put this. Put the values in, and so on. Because what you're deriving is, it's not clear. It doesn't show clearly whether you really understand what's going on. Okay, so this is just a sample block diagram. This is how you should be labeling it. Yeah, put in, because there's been a lot of instructions given to you to put in, use the exact variables, put in the transfer function. Yeah, so please do it and not just give any generic labels that's in the book. Okay, now I want to ask you this. Which one is servo? Which one is regulator? Problem. Can you label this? Now, there's not all of you is in Jamboard. Please come into Jamboard now, because then you can participate. Which one is servo and which one is regulator? By the way, if you choose to answer, and if I know who you are, the first one who turn on your mic and provide the answer, 4 questions that I ask, you will get a bonus for your quiz. And many times you have not been doing that well for your quiz, so the bonus will really help you. But in this case, just label which is servo and which is regulator. Come on, everybody. Okay, there's one answer there. That's servo, betul ke? Is that correct? Okay, you can use sticky notes or you can type, whatever, tak apa. Just try. Put your answer there. Okay, so most of you say that the bottom one is regulator, but for the top graph, some of you are saying that it's somebody says regulator. Most of the answer is servo. By the way, are both responses stable? This is after a step change, Are they stable? Both of them? Yes or no? Yes. Oh, you don't want to say anything. Why is it stable? Which one is stable? Both stable or only one of them stable? You can unmute your mic, if you want. Both stable ke? Is it both stable? Okay. Yes, because both are bounded, Okay, very good answer. So both stable because they are bounded. Okay. So yeah, both stable because bounded, So that's very important. Yeah. So this is actually servo. Why do you say this is servo? This is correct. Why do you say it's servo? How do you know it's servo? You can unmute your mic if you want. Because it's set point change. Okay, so if this is a control variable response, you have it changing to a new set point. Okay, so it's servo. What about the other one? Why do you say it's regulator? We don't see the disturbance change, but the set point is still trying to stay where it originally is. Okay, so we are not detecting any change in the set point. So if the control variable is oscillating like this, is having a response, then that means there is a disturbance that has entered. Otherwise, it would have gone on to the new set point. Okay, so that's why it's regulator. Okay, very good. Now, which one of this, which is stable, which is not stable? Which one has a pole that with a positive real part? has at least one pole with at least with a positive real part? Which one has at least one pole with a negative? It's negative. Is a negative real part. Alamak, let me edit this. Okay, unstable. Very good. Now, think about the poles. Poles is in the numerator or denominator? Poles are in the denominator. So the poles must be positive or negative for it to be stable. And how come you guys do not want to unmute? Yeah, you just like to do this. You prefer to write on the Jamboard. Okay, so the poles must be negative. Yes, betul. Good, Ain. So the poles must be negative for it to be stable. Okay? Okay, good. The real part must be negative. Okay, very good, very good. Very happy to see that you're able to understand this. Now, among you can see that there's four responses. This one is one response. Alamak. I keep forgetting that this thing can move. Let me. Okay. Now, we know that there's two responses here. This is also unstable. The green line here is also unstable because it's unbounded. Now, which one of this, there's two responses here. There's two responses in each graph. On the left graph and the right graph has two responses. Which one of these responses has complex roots? Complex number as the roots. Can you identify it? Which one has complex number as the roots of the poles? The poles is complex. It's a complex number. Which one? Complex number, complex number. Okay, so this would have both complex number as the roots. What about this one? What about the one on the left? The unstable one, yeah? But this is also unstable. The other graph, this one, the other curve, this is also unstable. Yeah? Does it have complex poles? Which one has complex pole? The second, which one? Which is the first? Which is the second? Alamak, can you unmute and say it? Now, the red one or the blue one? Or both of them has complex roots? if you say the unstable one, both of them are unstable. I'm talking about the graph on the left here. Both of them are unstable.
Doctor, is it the red one, doctor?
The red one that has complex roots.
Yeah.
Yes, correct. Yeah. Now, the other one, the blue one, the turquoise one, although it is unstable, it doesn't have a complex root. Anything with a complex root will result in oscillations. That is how we know. Okay? Boleh So very good. I think many of you know. Do we do the next one? Never mind. We will stop first. I will explain first and then we'll go there. Okay? So we'll go to the PowerPoint first. Okay. So very good. You're able to recognize this. Now, let me show you the book. This is the Seaborg book. You can also refer to the Stephanopoulos book. It doesn't matter. But I want you to draw to you some of the things that's important for you to pay attention to in the book. Yeah. So the response that is oscillatory with the amplitude growing in each successive cycle. This is the definition of something that is unstable. Yeah. Kejap. Okay. So unstable response, you have, it's oscillatory with the amplitude growing with each successive cycle. But with an actual physical system, the amplitude will increase until there is a physical limit. Now, if we do the mathematics, it seems as if it will grow and grow and grow and grow until infinity. But with real things, there's always a physical limit. For example, if you have a pipeline and you have a valve, yeah, so the valve cannot open bigger than the pipeline. Yeah, there's always the maximum limit of the diameter of the pipeline. And if for valves, if you keep asking it to open until the maximum, then it will fail very fast. Yeah, the valve can get worn out very fast. So this is what is meant by equipment failure. So the final control element always has a saturation limit. So saturation limit meaning that it has reached the maximum and it cannot go beyond that anymore. And anything above that will not be able to take action anymore. And we say that it is already saturated. Yeah, it's already at its maximum limit and it cannot go beyond that. Okay, so an unstable response will manifest itself as a sustained oscillation with constant amplitude. So sometimes even though it is constant amplitude, you don't see it increasing, it cannot increase anymore because physically it is impossible to increase. Okay, so sustained oscillation can also will also happen. Yeah, will especially happen when the final control element is saturated. Okay, so for a feedback control system to work, you cannot have the final control element saturated. You cannot have the control action to be so large that it will force the final control element to reach the maximum. Now, final control elements can be something other than also control valves, because control valves, although control valves tend to be the most common final control element in a chemical plant, you can also have certain variable speed pump where you can control the motor speed to be the final control element. Yeah, you can also have the compressor. Yeah, compressor where you can control also the motor speed to be the final control element. Okay, so there are other possible final control elements. Yeah, so it's not necessarily that you will have a valve, because sometimes when you want to control the vacuum pressure or let's say a cooling system, so it may involve a compressor. Okay, but most common is a valve. But don't think that you have to manipulate a valve all the time. Okay, so it is of course of practical importance for you to know that that is why we need to have an idea of in which region that the system become unstable. Okay, so we feedback controllers are easy to operate, but we have to know in which region it becomes unstable. Yeah, so this, if you're able to estimate using a calculation like this, then it will be very useful, especially when you have to do the tuning. So I'm sure all of you have read this, but the general stability criterion. Okay, so we have said that. Now, most industrial processes are stable without feedback control, but there are some systems that can be unstable without a controller. Okay, so we call them as open loop unstable. If they are stable without having controllers, then we call them open loop stable or self-regulating. It can regulate itself to reach a steady state. Okay, but if a process, let's say an exothermic chemical reactor, if you have exothermic reaction, the temperature will continue to increase and increase and increase until it go up, and the reactor can explode. And it's the same for one of the systems that you saw, because for your case study 3, because we put a valve at the outlet, so you have an inverse response. Sorry, not an inverse response, a pure integrator. So a pure integrator theoretically, is an open loop unstable system, because if you let it grow, it will go over and go on to infinity. But if it is being manipulated, then of course it can become stable. But on its own, it becomes an open loop unstable system. It's a non-self-regulating system. Okay. So the definition of stability we have seen just now: an unconstrained linear system is stable if the output response is bounded for all bounded inputs. Otherwise, it is unstable. So if you have a positive pole, this is what will happen. It becomes unbounded. It goes to exponent. So just in general, if you have the poles and the zeros, poles will determine whatever it is regarding the stability of the system. The zeros will determine the transient response, the type of response when we are changing the process, the dynamic response from one state to another. Poles will influence what happened in the final response and also in the transient response, but poles will generally determine the stability of the system. Okay, so for a closed loop feedback control system, you will have this feedback control equation. You know how to derive this already. So this is the characteristic equation, and from this characteristic equation, we can get, following a step response, we can get this. We can get the poles and the zeros. Normally, if you have a higher than second order, it's a higher order system. So you can see that if you have a pole that is positive, it will, when we change the Laplace domain to the time domain, you will see that it will have a positive exponent. So even if it's only one positive root, it will result in a one positive exponent. Okay, and finally, this positive exponent will cause the response to go up to infinity. Okay, so that is why the pole must be negative. If it is positive, Yeah, if you have a pole that is negative, so this is negative exponent to the negative. If it's exponent to the negative, then it will be, this is the contribution of that negative pole. The contribution of a positive pole will be in this manner. So it will finally drive everything up. Like our COVID case, yeah, if we do not go to lockdown, it will go up like this. We were already going up in the, almost reaching the vertical line. So that was why it was very dangerous. People do modeling also for the COVID infection. So they were looking at the exponential curve with what was happening in Malaysia, and what could happen. So anyway, for the general stability criterion, a system is stable only if all the roots are negative, which means that they have negative real parts. You cannot even have one of them with a positive real part. Okay? You can see the contribution of the positive pole. Okay, so now, if we plot the imaginary number versus the real number, yeah, so because this is the real number axis, we need the poles to be over here. Yeah, anything in the shaded region, that means it is unstable. Okay, so the feedback control system is stable if and only if all roots of the characteristic equation are negative or have negative real parts. Otherwise, it is unstable. So I want you to do an exercise on Jamboard. Go back to that Jamboard. And I want you to plot the poles with x's, with an x. So which one is stable, which one is critically stable, which one is unstable, and you just plot which part is with an x, with a small x. Okay. Where do you think is the pole? Which one is unstable? Which one is stable? Okay. Yes, that is unstable. Is it? Others? All the others stable, or are they unstable? Okay. Label it as stable, critically stable, or unstable. Which one is critically stable? Which one is stable? Which one is unstable? Okay, come on, you should try, because it's okay to be wrong. Even if even if you guessed it wrong, just think of why you think it's stable or unstable, and just try, because at least even if you're wrong, nobody know who you are, and at least it will help you to remember even more. Okay, even if you got it wrong, if you got it right, then it will also help you to remember. Don't just sit quietly and think to yourself. Okay. Okay, I want to ask you, what is the meaning of critically stable? What is the meaning? We've seen the meaning of stable. What is the meaning of, I think basically all of you got the unstable correct. Which one is critically stable? What is the meaning of critically stable? Anybody? You can unmute your mic, yeah? Anybody want to guess? It's okay if you don't have the perfect answer, but then at least give a clue so that others can build up upon your answer. What is critical stability? What is critically stable?
Doctor, is that mean there are no errors like that? There are
No
just
errors.
zero errors here.
Doctor,
No
is it
errors.
going to stable?
Critical. Now, critically stable is when if you increase the gain even a little bit, after that it becomes unstable. Okay, it's on the borderline, just before instability. Okay, so which one is critically stable? Are you all happy with the answer? Yes? No? Do you agree the first one is critically stable, everybody?
Oh,
Huh?
uh,
Oh, we change to that.
the first and the third seem to, for me,
Hmm?
seem to be similar for me. I don't know how to differentiate
You don't know how to differentiate.
between both rough. Yeah.
Okay. The top one and the bottom one.
Yes. Both I think is stable, but I don't know how to
Okay.
differentiate.
Okay. Which one has the same amplitude?
Third one.
The
That
bottom
one.
one.
Yes, the bottom one has the same amplitude, right? This one is getting smaller, almost same amplitude, but it's getting smaller and smaller. Yeah, if you compare this and this, it's smaller. So it is going smaller. So actually, this can be said to be stable. But this one, if you it is exactly the same. So this is a sustained oscillation part. So when you have sustained oscillation, that means it is critically stable. This is where the gain is at the ultimate gain. Yeah. Kalau if Ziegler-Nichols, this is your KCU. Remember? Yeah, you tried Ziegler-Nichols kan? So this should be your KCU.
The
Now,
one yang again to a prof.
yeah, the ultimate gain. This is
Okay.
where your ultimate. So if you increase just a little bit, it can become like this. You can see my where I'm pointing, right? Can
Yeah,
you see?
doctor. Yeah, yeah.
Okay, I use a laser. Okay, you can see here. So this is where the amplitude is the same. Yeah. But this one, it is going down. Oops. It is becoming smaller. Okay. Now, when you have imaginary roots, you have the real part is the same, but the imaginary part also has the same number, but it's a positive and a negative. So generally, it's a pair. Yeah, you have to have one pair like this and this. Where do you think the pole is for critically stable?
At the y-axis.
Great. Very good. Very good. Very good. Yeah. This is where it is. Yeah. Right on the axis. Right on the axis. Yeah. There's no real part. It's zero. Yeah. Right on the y-axis. It only has the imaginary number. Now, the moment it increases a little bit, it will become unstable. Okay, the moment you make it a little bit smaller, then it becomes stable. Very much like this. Okay, do you understand? Okay, now you have the laser also. Okay, faham tak ni? Do you understand? Yeah.
Yes.
Now, what if, let us look at the next one. Now, what if you have a response like the top graph or the bottom graph? Can you plot the poles? Okay, now there's several poles. Okay, good try. Anybody else? Which one do you think is the answer? Which one is correct? We have correct answers there. Which one is correct? Yeah. Okay. So for both poles, it's on the axis, yeah? Except that for this one, yeah, this one is stable. So the pole has to be on this axis, yeah? There's no oscillation, so the pole do not have any imaginary parts. Okay, that is why it must be on the axis. In this case, this is not oscillatory either. So it is positive, but since there's no oscillation, it has to be on the axis. There's no imaginary part. Okay, so you know that it's unstable, so the real part is positive, but you can see whether there's the roots, the pole has imaginary number or not based on whether it has an oscillation or not. Okay, do you get it? Boleh tak? Okay, so we will stop this first. We will go to it. Alamak, I need to finish up the closure fast because we are going to the next part. Tuning, So everybody clear? Anybody have any question on stability? Basically, from the book, you can see the root stability criterion. Yeah, hold on a minute. I need 1 minute. Okay, sorry. Now, so basically, the root stability criterion is very important because we need to, what basically we need to know if something is stable or not is if the pole has a positive real part. Okay, so what the root stability criterion tell us is that we can check for this positive real part of the poles if we do this the two steps. So from the root stability criterion, first of all, you need to look at the characteristic equation. So if there is anything missing or if there's any negative numbers for the coefficient of the polynomial, then it is unstable. So you don't have to go to the root array. But if everything is positive, then you need to do the root array. Okay, so everybody understand that if it's negative, if you have date time, you have to use Pade approximation. Sorry. So that's Pade approximation. If you have time delay or date time, the date time has to be replaced by a Pade approximation. Okay, so this is a first order or a second order Pade approximation. Normally we just use the first order. Normally this is sufficient. So okay, normally this is sufficient. You don't have to do the second order. This is fine. Okay, so the Roth stability criterion is, I think it's simple enough. This is the equation. Yeah, all this has to be positive. If it's positive, then the system is stable. Okay. Any questions on Roth stability criterion? Fairly straightforward. Just the two steps. Check for the coefficient of the polynomial first. If you have date time, make sure you change it before that. And then if it passes the first test, then you go to the second test. So the second test is the Roth array. Okay. So now for tuning, basically there's lots and lots of methods for tuning. Okay, tuning, basically we want to find the tuning parameters for the controllers. Normally when you use tuning methods, these are just approximations, estimation to get the first value. After that, you still need to do fine tuning. You still need to make small adjustments from that initial value that you have. Now, if we have a proportional integral derivative control, so this is normally when we buy feedback controllers. Yeah, any feedback control, standard feedback control, we will have all PID. All PID will be there. Yeah. The parallel form is one of the most common ones, but you do have other forms. But the behavior is the same. You just have to look at the equation that it is representing to understand how to do the tuning. Yeah. Sometimes you don't have tau I here to give the value. Sometimes you have the whole thing 1 over tau I. So you have to know the effect of it. Okay, now this is the block diagram representation. So basically this is what we're tuning. KC, tau I, tau D. Now, if let's say I only want a P control, proportional control, what do I have to do to tau I and tau D? Anybody?
To 0.
Set what to 0?
The value of tau.
Which tau? Which tau?
Tau D.
Tau D. Okay. You set tau D to 0, then there's no derivative action. Okay. So tau D to 0, no derivative action, right? What about the integral part? What if we want to eliminate the integral part? What should we set tau I to?
So infinity.
Infinity. Can we set as infinity in the real world?
No.
As big as possible. Yeah. In the real world, we cannot set to infinity. So whatever is a very large value, so set tau I to that very large value. Okay, so that this will minimize the integral part. Okay. Yeah. Okay, very good. Now, this is the answer for the case study 3 for the level controller. So you have the level controller here for the flash tank, yeah, flash drum. So there's an this is a pneumatic valve. The system is electronic, but you have a pneumatic valve. That's why there's a current to pneumatic conversion. But it's just one. So this is a block diagram. And like I said, make sure when you do anything, you label and put in the whatever that is that you have found from the estimation. Okay, so this is pure integrator. That's why the equation is like that. Okay. So basically, you can estimate the slope from both of this and take the average. Yeah. So you can estimate the positive slope, negative slope, and then take the average. You need to divide it by the step change. Yeah. So if you divide by the step change, then it will come out you will get the gain. Okay, this is from one of the tutorials and quizzes. Yeah, again, this is labeled and you put everything inside the block diagram. Okay, you need to show all calculations. Now, if you are making model estimation from the graph, please show where it is. Yeah, you need to show which point you are taking, because that is part of your working. Now, you have, when you want to tune, there's two types of problems. You have correctly identified just now the servo and regulatory problem, regulator problem. So let's look at Jamboard to see if you can identify all of them. Where is my Jamboard? Okay, this one. Okay. Now, which one is servo, which one is regulator? This is P control. So you have to remember P control will have offset. Which one is servo, which one is regulator? Anybody? Make a guess, make a guess.
The first one is servo,
First one is servo, second one?
regulatory.
Anybody else? Thank you very much for your answer. Okay. Okay. So most of you say that first one is servo. Why do you say it's servo? Actually, it's very easy, and you can see the new set point, and the response is trying to reach the set point. The higher the KC, the smaller the offset. Yeah, you can see that the higher the KC, the smaller the offset. But there's still offset, because this is just P control. And for this, there's no set point change. So obviously, this is regulatory problem, regulator problem. So even though there's controller, when the disturbance enter, it will still go up. It will still go. It will still move away from the original set point. Okay, so this is where the initial set point is. This is where the set point is, not just the initial set point. The set point is not changed. Okay, so since the set point is not changed, but still the control variable has moved away from the set point, because with only P control, you will get offsets. Okay. By the way, you do know how to use the final control element, the final value theorem, Okay, which one is servo? Which one is regulatory control? Which one is servo? Which one is regulator? What is that one? What is this graph? Anybody? Regulator. Everybody, do you agree that it's regulator?
Agree.
Okay. What about this one?
Servo.
Is it servo?
I think so.
Why?
Because
You see the is there a new set point? This is PI control, That's why there's no finally at the new finally the yes, set point come back to 0. Yeah, the set point did not change at all. Okay, so this is regulator, this is regulator. What about this one? Regulator or servo? This third graph. Is there when you know that something is a servo when there's a new set point being set. You know something is regulator when there's no change in set point, but the control variable is moving away from the set point. Yeah, so that means a disturbance has entered the system and disturb the the control variable. What about this third graph? Is it servo or regulator? Which one do you think? Ain, any guess, Ain? What do you think?
wait, doctor. I need to think first.
Servo, Prof.
Servo. Yes. Ain? Thank you. Lagi? Servo. Okay. Servo, because you see that the control variable, this is the new set point, 1, So the control variable is trying to reach there. Yeah, so the higher the gain, you can see that it begin to oscillate. But after it reach a certain point, it has reached beyond the stability limit. Okay, but it's slightly off than the new than the new set point because this is just P control. Okay, on the other hand, this is PI control. By the way, PI control is easier to make the system oscillatory, to have an oscillatory response because of PI controller. Okay, but P control usually it can be fast, but because of the you will get offset, but it is more difficult to make it oscillatory and to make it is you can have a bigger gain with P control compared to PI, because when you have PI, because you have one more S, that can push it to the non-stable region very, very easily. Okay, so I think that's it. with the activity. We'll go back to the slide before we go for your quiz. Okay. So you've seen this. Now, when you do an offline or online method, usually, and the offline method, you can also call it as a process reaction curve method. So you get the process response. This is the reaction curve. You get the process response and you estimate a first order plus date time model. You can actually estimate the FOPDT model using different ways, but the 28%, 63, not 68, alamak, sorry, 28%, 63% method is very common. Okay, so you can get tau and the date time just from 2 points. The inflection point method is slightly more difficult to get the FOPDT model because it depends only on 1 point, and getting the exact inflection point and getting the tangent is quite difficult. Okay, so my advice would be for you to use the 28%, 63% method. Yeah, if you have the time, get three or four data points, then you can use the other method, the graphical estimation method. Now, if you want to do this in real life, when you do the lab or when you're in the plant, normally the offline method is not that favored because you have to take the system offline. Yeah. When we say we take the system offline, it means that you take off the controller. You turn off the controller. Okay, there's a switch. Actually, you don't pull out any wire. You can turn off the controller and instead you go to manual. So turn off automatic control, you go to manual control, and from manual control, you can change the input to the valve. Okay, manually change the input to the valve. So if you want to make a step change if you make a step change to the valve, this is an actual process. You make a step change to the valve, then you can get the measured response. Yeah, so this is your control variable. So whatever it is, you cannot measure it here because there's no sensor. So most of the time you will measure it at the sensor. So whatever you measure, you estimate from the curve here, we call it as GPRC, G process reaction curve, which covers 3 transfer functions: GV, GP, GM. Okay, so you don't have to get any more valve transfer function, process transfer function, or the sensor transfer function separately. It comes together. Okay, so this is the output, this is the input. So when you are estimating this, it is actually GV, GP, GM. Yeah. However, for your case study, we do not have the GPRC, but instead we use a simulation. Okay. So if you are doing a simulation, it's so much easier to make the step changes. Yeah. So if you have the simulation and you make the step change in the manipulated variable, or if you make the step change in the set point, then you can actually get the GP. Normally, to get exactly the GP, you have to make the step change in the manipulated variable and get what is the output. Yeah. You can also make the step change in the disturbance and get what is the output. So this is the data that you're given in your, it's from a simulation. So from a simulation, it's so much easier to get all the response, these curves. Yeah. Okay, but if you're working with an actual process, it's actually GPRC, GV, GP, GM. So when you get a process reaction curve, when you get a first, let's say you get a first order plus dead time curve, you need to know whether it is from a simulation or if it's from an actual plant. If it's from an actual plant, then this is a transfer function that you are looking at when you estimate the curve. Okay. But if it's from a simulation and it says this is a process simulation, then that means this curve, if you estimate the model, you're getting GP. Or if they say that the step change is on the disturbance, then you're getting GD. Okay, understand? So this is what you had done in your case study. Everything was from the simulation. So actually, when you have in your case study, you have 2 inputs and 2 outputs. And there will be, this is part of a system. So when you change for the level, it will affect the level controller. Anything to do with the level controller, it will also affect the temperature. When you change anything with the temperature control, it will also affect the level. Okay, especially when it has to do with the flow rate. So if you have 2 control systems, 2 feedback control loops, this can be the manipulated variable for the other control loop can be the disturbance for the other one. Okay, so you can actually do this in Simulink if you try. I don't know whether you tried it, but then well, this is what will happen. Any of you managed to do the Ziegler-Nichols method? Now, Ziegler-Nichols is actually very common. It's a very common method used in industry. So they will increase the gain whenever there's a process shutdown to retune everything. It's quite common in plants to increase it until it's almost cyclical, and then use Ziegler-Nichols, or if it's too vigorous, they will multiply it by a smaller number. Okay. Now, by looking at the Ziegler-Nichols tuning parameters, now Ku is the ultimate gain. So Ku, when you calculate the stability using Routh stability method or the direct substitution, this is at Ku is the gain at the critical, where that critical stability is. Okay, the ultimate gain is where you have the process at ultimate stability. The critical stability, the ultimate gain. So for P control, you cut it in half. For PI controller, because it's easier to become unstable, we multiply it by a smaller number, 0.45. For PID, the derivative mode is actually a stabilizer because it has anticipatory action. It can anticipate what's going to happen because of that derivative, the DE, DT. We talked about this in the closure for 3A. So that's why you see it's being multiplied by 0.6. So among the 3 controllers, if you follow Ziegler-Nichols, the derivative, the PID controller would have the biggest Kc value. Okay. Now, Ziegler-Nichols is actually the criteria when it's derived is for the response to have 1/4 decay ratio. So it's quite vigorous for chemical processes. So sometimes we will make it smaller, especially for the fine tuning. Okay, so this is a continuous cycling in Simulink for the level control. Again, this is level control, which is servo and which is regulator. This two is for the same tuning, but with fine tuning. This one of it, the top one is the original from the first estimation from the calculation. The bottom one is after fine tuning. Which one do you think is servo? Which one is regulator? The one on the left? Which one is servo? The one on the left or the one on the right?
Left.
Left. Alright. Seorang aja cakap.
The right is regulator.
Huh?
Right one is regulator, the left one is servo.
Okay. Anybody else? Okay, thank you, Hafiza. Anybody else?
Doctor, left one is servo, right one is regulator.